quick review on the first paragraph there. A force from the last couple of days. You could use the definition of force as like either a push or a pull, but that's like a grade 10 definition. So better definition, a force is something that changes an object's velocity. Does that make sense? If a force then changes an object's velocity, change in velocity is also known as acceleration. Yeah. So Newton discovered this and realized there was a relationship between this. And some of you guys know this term because you were in my chemistry class. Some of you guys don't know this probably term yet, but it's called an inverse relationship. And you guys, we actually talked about this a little bit yesterday in math as well. An inverse relationship is kind of like a teeter-totter, like a seesaw, where if one of them goes down, the other one has to go up. Does that make sense at all? So here's his idea. There's an inverse relationship between the mass of an object and the acceleration of the object. And I hope that kind of makes sense. Imagine that I'm trying to push something light across the desk. I can accelerate it, it's not that hard. But what happens if I'm trying to push all four of these things across the desk? Well, now there's more mass. Will I be able to actually push them as fast? Probably not. So I mean, extrapolate that to whatever it is you're thinking of. Like, you're pushing a boulder. The heavier it is, the harder it will be for you to actually get it to accelerate. Does that make sense? So that's called an inverse relationship. If mass increases, acceleration will decrease. Or if mass will decrease, acceleration will increase. Can you grab that door? Thank you. I don't know that I've shown those of you in grade 12 this symbol yet here. This symbol means like proportional to. Yeah, that little A. Proportional to. So essentially what this means is the acceleration is proportional to 1 divided by the mass. Okay, which is an inverse, or sometimes we use the word reciprocal. Michael, could you grab that door too? Apparently it's like hammering session outside. Okay. Here's some graphs I'd like you guys to know. If you were to say make a graph of force compared to acceleration, well, the more force you apply, the more acceleration there would be. Does that make sense? Like if I push harder, in theory it should go faster. We call this thing a direct relationship. What's a direct relationship? It's a linear graph. And I think most of you guys have seen linear graphs at least at some point in your life. You better have, otherwise you didn't pass math 10, I think. Okay. This is a graph that we cover in math 20-1. So some of you guys have seen this, some of you haven't. This is an inverse proportional relationship graph. This would be the graph y equals 1 over x, which is what we did yesterday in math 30 for some of you guys. Okay. These graphs and these relationships, we don't probably need to have the math background exactly yet to figure it out, but as we get to reciprocal and inverse relationships, hopefully you'll kind of recognize the patterns with math and how these guys fit. Does that make sense at all? So if you were to compare force and acceleration, the more force you have, the more acceleration you have. That's a direct relationship. If you were to compare, though, mass and acceleration, the heavier something is, I shouldn't say the slower it goes, but the less acceleration you can give the object. Does that make sense? So I do need you guys to know these terms because they come up quite a bit. Direct and inverse. This is like the graph y equals x, and this is like the graph y equals 1 over x. Okay. I promise, if you're in my 20-1 class, we're going to talk about this graph eventually. Okay, so please don't freak out if you're like, I don't know this yet. Newton basically then discovered a formula by putting all of this together, and this one is written on your data sheet, but slightly differently. They didn't write it as, where is it here? They didn't write it as F equals MA. They wrote it as A equals F over M, if you have your data sheet nearby. But it's the same formula, just rearranged. So his concept here was any net force is going to be equivalent to the mass times the acceleration. So fairly straightforward, only 3 variables, not a lot to worry about here. This guy right here is the most important one though. Okay. It has to be the net force. So you can't just use this for any one random force like force of gravity or normal force or friction force. It has to be the net of all forces is equal to the mass of the system times the acceleration. In terms of units, mass has to be in kilograms. Acceleration has to be in meters per second squared. And the unit we've been using so far for force is going to be in newtons. And so just so you know, a newton, like 1 newton, is equivalent to 1 kilogram meter per second squared. But that's what a newton is actually equal to. It's equal to a kilogram times a meter per second squared. It's kind of a weird unit. That makes sense so far? Okay, one last thought here. Force is a vector. So like we've been doing in our original problems here, sometimes I'll give you questions where something goes like this way and that way, and you don't have to worry about angles. Sometimes. But most of the time, we'll have a force that sometimes goes like this way, and then one that goes this way, one that goes that way, and you're going to have to break things up into like x and y. Okay, so that's not going away, that whole trigonometry aspect. So let's do a couple examples. You've got a car, and I tell you how much force the engine is able to move it forward. So you have a 1,250 kilogram car. You apply, what is that going to be, about 351 newtons worth of force. Can we figure out its acceleration? And yeah, this is going to be the net force, yeah. Good question, right? We got to ask, is that all the forces applying on it? So based on the scenario here, yeah, that's all I'm going to give you for that. So your net force is equal to your mass times your acceleration. So this is 351 newtons. This is 1750 kilograms times acceleration. How do you get acceleration by itself? Divide out the mass. Units get a little bit tricky when you're working with newtons because it looks like you're going to have newtons divided by kilograms. So sometimes it wouldn't hurt to remind yourself, like maybe write this on your data sheet somewhere, that a newton is the same thing as a kilogram meter per second squared. So when I actually write this out, you could have written it out as 351 kilogram meters per second squared divided by 1250 kilograms. And that way you can see the kilograms canceling, and the only units left would be meters per second squared. So I just need to grab a calculator. .351 divided by 1250. I got 0.28, but I get 3 sig digs. I'm going to start being a little more picky with sig digs. I've been fairly lenient on them so far. Make sure you're watching carefully from now on. So you should get 0.281, I believe, meters per second squared. And one more thing, we do have a direction for this acceleration.
Forward.
Yeah, you could call it forward. Again, these are vectors, so direction definitely matters. Would be weird if somehow you were going backwards. I guess the car would be decelerating. That doesn't make sense. If you're pushing it forward, it shouldn't be decelerating. What's that? That's true. We'll get to that actually. We've got questions like that where we start going up inclines. Good point though. Okay. Any questions on that one? Okay, that's a really basic level question. I probably won't ask you many of those. Those are pretty straightforward. An elevator question is a typical question you might get asked though. Imagine there's an elevator and I can tell you how much there is total in the elevator weighing it down, and it gets raised by a cable that exerts a force up. We want to find its acceleration. Do you guys remember the term free body diagram? Okay. Well, a free body diagram would be like me drawing a box, I guess, and saying this is an elevator. There's a cable pulling this thing up. Fantastic. I could call that the force of probably tension. It's probably the most common word we'd use for that. There's tension in the cable pulling it up. Is that the only force acting on this though? For sure, gravity's acting on it. And so I often won't tell you that gravity is acting on an object. We're going to have to, I don't want to use the word assume, but does that make sense? Like, it's not going to be straightforwardly like said to you. You're going to have to realize, hang on, gravity always acts on objects. So in this example here, you've got tension pulling this thing up, and you've got gravity pulling this thing back down. Does that make sense? So if we want to find the net force, the net force is going to be, well, tension is pulling this thing up, and gravity is pulling it back down. We have to take that into account, yeah. So I already know what the tension force is. The tension force is 4.0 times 10 to the 4 newtons. We now need to figure out the force of gravity. Now, you guys have, I believe, done this back in grade 10. Does anybody know how you calculate gravitational force? Have we done this in this class yet? It's mass times gravity. It's 9.81 times your mass. If you don't remember this formula from grade 10, the force of gravity is mass times gravity. So we know the mass of the elevator. It's 3710, or no, 3700. And gravity is 9.81 meters per second. Did you guys remember this formula from grade 10 at all? It's probably been a while since you've done it, though. If you don't remember it, write it on your formula sheet. To find the force of gravity, it's mass times the gravitational constant. It might even be on your formula sheet. It is too, actually. It's rearranged though. It's g by itself equals fg over m. G equals fg over m. That formula is on your data sheet. So, okay. So how much force is gravity actually pulling this down by? 3,700 times by 981. I got 36,297 newtons. Yeah, and to be more specific, that's pulling it down. Whereas the elevator is pulling up at 40,000 newtons. That's a U for up. So if the cable is pulling you up at 40,000, but gravity, if the cable wasn't there, would cause you to plummet, right? If gravity would cause you to plummet at 36,000, what's your actual net force? 40,000 newtons minus 36,297 newtons. So our net force is actually only 3,000 some newtons. Does that make sense? I'm going to keep being specific here, though. You are still going up, though, right? Because there is more force in the cable making you go up than making you go down. I'll do sig digs when we're done, though. Well, because our goal was to find the acceleration of the cable. You're right, though. Like, we should do sig digs, but I'm not gonna round any numbers if I don't have to until the very end. So, okay. So if our F net is equal to 3703, our F net is also equal to the mass of the system times the acceleration of the system. So I could say that 3703 now is equal to, what was mass again? 3,700 times A. So divide by 3,700. Divide by 3,700. It's going to be approximately 1, isn't it? Like 1.001, I'm sure. Pretty close. Okay, so now let's do sig digs. What do I get for sig digs? 2? Because this guy here only has 2. So we would say this thing's accelerating at 1 meter per second squared. In this unit here, we're going to have to be specific when we do accelerations as to which direction the acceleration is going. Because in this example here, the elevator is going up. That makes sense? It is possible that we're actually going to start getting some accelerations in the downward direction. Because that, what would happen if like the acceleration, the like the elevator were going down, then the acceleration could be going in the downward direction too. Cool. Sorry, what was that? Oh, way back at the top here, this 4.0 times 10 to the 4 only had 2 sig digs. So that's why I only got 2. So let me walk you through all the steps we had to do there one more time. First, I had to consider my free body diagram and recognize that my net force was not just the tension that was given. I actually had to subtract gravity because gravity would be pulling the elevator down. I have to account for that. So the tension minus gravity, which I had to figure out what gravity's force would actually be, gives me my net force right here. Once I have my net force, then I can make that equal to m times a. Does that make sense? So what originally might have seemed like a fairly one-step forward problem wasn't actually one step at all. That's probably breakfast. Let me grab that. Come in.
Like, do you want me to?
Sure. Hello? Breakfast? Anybody? You guys can just open the door and come in. I'm not scary, I don't think. Okay, one of those actually.
Hey, no banana.
Vanilla. There we go. Last year I had like Brennan trained. You'd always have that one sitting aside. Thanks, guys. I know, isn't it? But the afternoon, it's just sweltering. Would you mind closing the door on your way by, though? Thank you. Okay. Any questions on the example here? Okay. I have a follow-up question then. So the follow-up question is, well, what would happen if the tension was only 3.3 times 10 to the 4 newtons? Yeah, because think about our net force. Our net force was going to be equal to, we had some that was pulling up and some that was pulling down. If this guy is 33,000 newtons, what was gravity though? Wasn't it like 37?
Oh, yeah.
It was 36. 36, 297. Poor Carla. Okay, does everyone get the twist I'm throwing into this question here? I might not tell you the elevator is going up or down, right? Because what's happening here is that obviously however much the motor is capable of pulling the elevator up, it is not enough to overcome the fact that gravity is pulling it down more. So our acceleration is going to be negative. This means one of two things. Okay. It either means that the elevator is actually plummeting, which is probably not good, or chances are what it means is that we're actually like it's braking and it's slowing down. Does that make sense?
What do you mean it's braking?
Well, like a negative acceleration could mean that the elevator is just slowing down. It's still going up, but it's slowing down.
Elevators do have to go down.
That is possible too. Like I don't actually know whether it's going down or whether it's just going up but slowing down. You guys get the difference there? So we don't actually have the information to know that, but chances are what's going to happen here is our acceleration will be negative.
Can you not have like a direction by the end of this?
Well, we'll just say that the acceleration then is going down then.
Okay.
Yeah. Okay, a couple questions here.
Did you just use for the force of gravity? Did you just use the
Yeah, exactly. Yeah, I didn't really need to recalculate it because it was the same question. Lisa, did you have a question too? Oh, no, okay. Okay, so for our force net this time around, I might do like say the 36,297 minus the 3,300, the 33,000. And this will give us what, 3,297? But now the acceleration is down. So like I said, one of two things. Either the elevator itself is actually moving down and is accelerating in the downward direction, or the elevator is still trying to go up, it's just it's slowing down. Does that make sense? Those are the two options.
Wait, one second.
Sure.
Why did you decide to put it in that order?
It doesn't really matter. I could have done the other way around and it would have given me a negative number. All that matters though is that you keep track of the direction. The acceleration direction is down.
So if it was a negative
So yeah, you could, okay, so here's two ways of putting it. You could say that it's a negative number and going up, or you could say that it's a positive number and it's going down. Both would be a valid way of putting it.
How do you determine it's going down?
Because there's more force on the downward side than there is on the upward side. So, one last step then. Take that 3297, make it equal to your mass times your acceleration. And it's going to be slightly less than 1 this time.
Can you guess exactly?
What am I, a calculator?
That's what it seems like.
Oh, sorry. I got 0.89. Okay. So here's your two options. You could say that it's going 0.89, I should put units in there, meters per second squared. You could say that its acceleration is 0.89 meters per second squared down. Or I would accept you telling me that it's going negative 0.89 meters per second squared up. Both of those would be a valid way of answering it. Again, I don't actually know whether the elevator is plummeting to a free fall, that's a possibility, or whether the elevator is actually going up but just slowing down. Does that make sense? We don't actually want elevators to accelerate upwards all the time, right? Because if it keeps speeding upwards, it would then like rocket out of the roof, right? So like at some point, the elevator will have to slow down a little bit so you can stop at the floor you want. So. All right, questions? Okay. Okay, here's another common type of problem that you might get asked. It's another system question where now you're going to actually have like a box tied to another box. You've actually got like two items directly next to each other. Okay. And I'm going to throw another number in here for you. I'm going to tell you that there's going to be some frictional force as well. So now I've got to account for that as well. We're going to try to figure out the force being applied to the system if they accelerate at this rate. So the key to questions like this is, sure, there's a 25 kilogram box and a 5 kilogram box, and they're separated by a string. But essentially, you could treat this as though they're just one box that has a total mass of 30 kilograms. Does that make sense? I know that there's two different boxes, yes. But isn't like the sum total, couldn't you imagine that these guys are basically just one item? All stuck together? Okay. So yes, there are two boxes, but let's just treat them as one box. Okay. We're trying to pull them this way. What could I call a force being pulled on the string? What would that be? You could do that, yeah. You could even go with like FA for like applied force. I don't really care what you use, just make sure you're specific. So tension's going this way. Which way is friction going to go then? Yeah, friction is going to oppose us going this way, so the force of friction will be 250 newtons. Are there any other forces in play here? Yeah, gravity would be in play. Yeah, gravity would in theory be pulling us down. Now, I don't actually want to calculate gravity's force though, just so you know, because there is a force that's opposing gravity as well. Good, the normal force, yeah. And unless for some reason these boxes are so heavy that they cause the table to collapse upon itself, the normal force should be equal to gravity's force. So like whatever Fg is right here, I don't actually care, because Fn up here is the same as it. So I really only care about your friction force and your tension force.
Unless it was like suspended in the air.
Sure, I mean there are other ways of like, this is where your problem solving skills are going to have to be worked on, because like it depends on the context. In this example, yeah, it's on a table, but yeah, it's in the air, changes things. So, okay, in this example here, we kind of have to work backwards, because our goal is to try to figure out the force being applied to the system. And that's basically, I'm asking you for, what is this tension force? Like, what is this applied force that you're pulling with? Does that make sense? Like we're looking for this guy here. So I'm going to work on the other side this time. I know my mass, and I also know acceleration. I could find the net force. Does that make sense? So I'll just treat the two boxes as though they're one, so 30 kilograms total. I know how fast it's moving, so I know how much net force there should be. I got 82.5 newtons. Okay, that means that the net is 82.5. But friction is pulling back at 250. It means then that the tension force here better be bigger than 250, otherwise this thing won't move.
Would you just add them together?
You would add them together, yeah. Now, if you want to like write this out in step by step, you could have said this. The net force would be equal to the tension force minus the friction force. Does that make sense? We know the net force is 82.5. We're looking for how much tension we're applying on the rope to make it move. And we're going to subtract the friction force. So then, how do you get tension force by itself? Add the 250. By the way, if you don't want to show your work quite like this, and you get it, and you just want to add the number, I'm fine with that too. Okay. But like, this would be a good proof as to why. So, add 250. So, you must pull this thing at 332.5 newtons. Let's go with forward. I have to do sig dig still though, because I don't think I get 4, do I? 3? 3. So 333. Does that make sense so far? So this example here, it kind of worked from like the other perspective. I started by finding the net force. I then used the net force to figure out how much actual applied pulling tension force there actually was by just adding on the friction to, well, we need to compensate for the friction, if that makes sense. Questions? Okay, let's do one more, then we're going to take a break. This is a good example of a question where not every question I can give you is just going to be exactly like the previous one. Here what we're going to do is we're going to put two boxes on a pulley, and we're going to let them go. So like, look at the diagram here. You've got a 7 kilogram box on one side and a 12 kilogram box on the other side. What's going to happen? Yeah, the 12 kilogram box is heavier, so it's going to have more force. So it's going to pull the blue box down, and the yellow box will go up. Does that make sense? So our goal here, if you've read through the question here, we're gonna tell you how high the 12 kilogram box is above the ground. I'm gonna tell you that it starts with a velocity initial of 0, and we're gonna try to figure out the length of time it will take this box to hit the ground. We're gonna like combine kinematics and dynamics kind of questions together. So like, this distance from here to here is 8 meters. That makes sense? Well, if we're normally looking for time, I need to find some other numbers. We have the distance in the y direction, that's 8 meters. I also know the velocity initial in the y direction, it's 0. Normally we know one other number in the y direction.
Acceleration.
Acceleration due to gravity is normally 9.81. But this guy isn't exactly working just due to gravity, because like this 7.5 kilogram box on the other side is kind of like a counterweight. So we don't actually know the acceleration in the y direction yet. Our goal is going to be to find the acceleration so that we can then use it in one of our kinematics formulas to solve for time. Does that make sense? this object is not exactly free falling because it's got a weight on the other side slowing it down. So acceleration, according to like a kinematics formula, won't be 9.81. We're gonna have to look for the acceleration here. So I'm just gonna leave this stuff and we're gonna come back to it. Okay. To get that acceleration, we're gonna have to use this formula. And this acceleration is the one we're gonna use. Does that make sense? Okay. So now we gotta approach this from like, well, what net forces are acting on this guy right here? It's kind of tricky because this one's getting pulled down and this one's getting pulled down, I guess? Well, because like gravity is, like, how do I put this here? Gravity is pulling down on this box. And gravity is pulling down on this box.
But couldn't you just subtract the weights from it and say that it's like whatever that we just said earlier? And just use the forces from just like that bigger box?
That's one way of approaching it. Yeah, I think I get what you're meaning. I'd like to show you guys another method of solving here. I think yours is going to work. Can we talk about that one in a bit here? Okay. One way of approaching it is to kind of change the layout of the question. Would it make sense that you've got a 12 kilogram box attached to a 7.5 kilogram box? Only rather than me putting them like over top of a pulley, I'm gonna put them side by side. The 7.5 kilogram box is getting pulled in one direction by gravity. I'm just gonna call it gravity 1. But the 12 kilogram box is getting pulled in the other direction by gravity. You kind of see how I'm changing the problem here? Rather than having the pulley in the middle and have them both hang downwards, if I were to remove the pulley and just hold them side by side, it's like one box is getting pulled one way and one box is getting pulled the other way. Say that one more time? We're going to do that, yes. Yes, we are. Okay. But first I've got to figure out the force of gravity pulling in this direction. So the force of gravity in this direction is going to be the mass of the one box times by 9.81. Which is 73.575. This guy over here, his force of gravity will be 12 kilograms times 981. I got 117.72. It hopefully makes sense then that the heavier box has more gravitational force attached to it, right? So if I wanted to then find my net force, it would be equal to the 117.72 minus the 73.575. So I got 44.145. I'm just going to pause there for a second. Just make sure everybody gets that. So to solve this question here, I know there's a pulley. Ignore the pulley. Imagine that there's a pulley here, strings over top of it. Imagine that you just lifted the strings off the pulley. What's really happening is one box is getting pulled one direction, and the other box is getting pulled the opposite direction. Right? So just find how much gravitational force each one has and subtract it. Heather, you, I think, had a suggestion of subtracting the two masses.
Yeah, and it worked.
Yeah, what you could also have done was 12 kilograms minus 7.5 kilograms, which would give you a mass net of 4.5. And then you could have times that by 9.81 meters per second squared. And that should also have given you 44.145 newtons. So your method would work. That works. There are some issues to always trying that method though, because sometimes the masses, I hate to use the word always. You guys know that. Sometimes it's better to actually like set up a free body diagram of what the force was in this direction and the force was in this direction and subtract them rather than subtracting the masses. I don't know that I can guarantee that this will always make sense in every single scenario, but it does work in this one. Okay, well now that we know that our F net is equal to 44,145, it's equal to mass times acceleration. Now we can find our acceleration. So your F net is 44,145. What mass are we using?
I'm using
Both together.
The combined mass. Yeah, this has to be the mass of the system. It has to be the total mass of the system along with the net force of the system to find the acceleration of, again, the system. Sean?
For finding, like, say if we did another question like this, then we have to use the mass of the whole system again.
Yeah. So like the mass of the whole system here is actually going to be 19.5 kilograms. So 19.5 kilograms times acceleration. I got an acceleration of... Do you guys get what I'm saying when I suggest you need to really be clear as to where numbers are going to show up from? Because like, there's numbers everywhere, right? And that's just kind of where physics goes, is you're going to be calculating one thing to find another, to find another, to find another. And so you got to be able to keep track. So I got an acceleration of 2.26.
Yeah.
I'm going to write down a few more numbers though, because I want to use them all. 3,846 meters per second squared. Now, I think down is probably the most appropriate direction to use for this. Technically, I guess you could say that the yellow box is actually going up at that speed, and the blue box is going down at that speed, but it's the blue box we care about. So we now finally know our acceleration. So let me go back up to the top now. 2.263846. 2.263846 meters per second squared. So now, using what we learned from last unit, let's put it all together. We know the distance it's going to fall. In theory, I kind of am trying to say it's going to get starting from rest in the y direction, but it's not full-on gravity that's actually pulling this thing downwards, because there's like a counterweight on the other side. Does that make sense at all? Like, there's a lot of systems in the world which would use like a counterweight to make sure that you don't free fall, like an elevator, right? Because if the elevator were to snap or something like that, right, there would be another cable, hopefully, that would have, you know, like a pulley over top of it to make sure that you don't plummet to your death, right? So, what formula do I use with these guys then? I think so, yeah. D equals VIYT plus 1/2 AT squared. So this guy will be 8 meters. That's 0, so that's kind of useless. We need 1/2 of, okay, acceleration here, I gotta think about this. The distance is going down 8 meters. The acceleration should also be going down. So let's make both of those numbers positive. So 2.23, that number. I'm kind of running out of room here. To get t squared by itself, times both sides by 2, divide by the acceleration, and square root. So I'm just going to go right to an answer. I'm hoping you guys can handle the algebra better. Divided by, where is that number? 2.263846154. And then square root. With sig digs, I got 2 sig digs. I got 2.7 seconds. Normally something falling 8 meters would not take 2.7 seconds. But because of the counterweight on the opposite side, it's going to cause it to not fall with normal gravity. It's going to cause it to fall a little bit slower than normal.
Which number in the end?
Any questions? Yeah. Can we look them over in a second here?
Yeah.
Okay. Let me just do a quick recap here, and then we'll go take a 5-minute break. Sorry, I'm probably talking at you all day today, so we'll go take a 5-minute break. To solve this question then, ultimately we needed to start by kind of changing our diagram and recognizing that it's going in two different directions. We had to find our net force by subtracting the two gravitational forces, or the masses, that worked. Once we found our net force, we used that number to find, my goodness, there's so much work here, acceleration. And once we used acceleration, we then went back up to the top and used it to find time. Keep your work organized, okay? Hey guys, this next couple of questions are all going to involve a similar twist that's pretty common. We're going to talk about things that are on an incline. I always think of like a snowboarder heading down a hill. Okay. Here's an example here, pretty basic one though. We're going to put a box on an incline of 30 degrees, and the box is going to remain stationary. So I don't know if you can kind of envision this, but like you've got an incline, you put the box on the incline, and there's enough friction that it doesn't start sliding down at all. Okay. We want to try to figure out how much friction would be required to keep the box from sliding down the slope. I don't really give you a lot of numbers here. You actually get the mass of a box and an angle, and that's actually all you need. Okay. Here's a picture I actually thought I'd throw in for you, the free body diagram of what's actually happening. Okay. Here's a box sitting on a ramp, okay. And there are three main forces being applied to this ramp. There's friction pulling the box kind of uphill. Well, stopping it from going downhill at least, right? There's gravity pulling it directly down. And there is a normal force. Now this may seem weird, but the normal force is actually, it always has to be perpendicular to the surface right there. So it actually kind of goes off at a bit of an angle here.
Then why is the FG?
Okay, well gravity pulls things flat down though. But normal force is always perpendicular to whatever surface there is. Because what the surface is doing is the surface is pushing at a bit of an angle, but gravity is pulling flat down. Here's my question then. If this is truly the free body diagram, why is the box not going back up the hill? Because these angles are not perfectly perpendicular. It may be better, you guys probably can't, well, you can tilt your page a little bit here. See if this makes sense. Where's my select button? To consider it like this. The normal force is going this way here, which would make sense, wouldn't it? Because that's what normally we'd think normal force is going, directly opposite the surface. Friction is going this way. But gravity is kind of pulling it at a little bit of an angle. And so what we learned last couple of days is that what we could do is make a triangle out of this, where there is like a y component and there is an x component to it. Does that make sense? This FG in the y direction, what is it equivalent to? The normal force, yeah. Yeah, you could say that the force of gravity in the y direction must be the exact same as the normal force. This arrow here and the blue arrow up, they must be equivalent to each other. Thank you, Michael. Whereas if I want to figure out the force of friction, what's it going to be equivalent to? The FG in the x direction, yeah. You could say the force of gravity that actually applies in the x direction, it's equal to the force of friction. Do you guys see this? Like, does that make sense when I turn it slightly sideways? That you've got force of friction this way, normal force this way. Gravity actually acts on a bit of an angle here compared to the actual incline. Like gravity, yes, acts down, but since I'm tilting my paper, there's actually like an x component and a y component of it. No, this one said the box was not sliding down the hill. So because the box is not sliding down the hill, the gravitational force must be the exact same as the FGX. Heather.
Okay, so when we have to find the like gravitational force, you have to multiply 9.81 by the mass. Would that give you like the resultant? Or
That would give you this hypotenuse right here, yes. Yeah, so you're a step ahead of me. We can find the FG, either not an X or Y. That's equal to mass, which was 15 kilograms? Multiplied by 9.81. So 15 times 9.81. Though I get 147.15. So I think this is your question, Heather. That is the downward force. Like I know I'm trying to tilt my head here, but like that's what it would be pulling it straight down. Only I've tilted my page slightly, if that makes sense.
But then
Ah, good question here. Because we can't do anything in this triangle here without an angle. Okay. I need to kind of change my diagram ever so slightly because this one didn't do a great job of it. So just bear with me for a second here. If I were to take this red line right here, I can't actually lift it up, but if I were to draw it from like say here down to the bottom,
oh yeah, 90 and then.
okay, and then draw this guy down like this and this, draw it like this a little better. Would it make sense still that this is now your FGY, this is your FGX? By the way, I don't actually care what you call them, FGY, FGX. Sometimes I actually call this FD for the downward force. I don't care, just label them consistently. If this is 30 and this is a 90-degree angle right here, this guy right here would be 60 degrees. Does that make sense? Okay. Well, this, the way I've drawn it is on purpose so that this is also a right angle right here.
But maybe like yeah.
Which means this little guy right here is actually 30.
Wait, what did you just say?
Okay, let me try that from the top there. I'll just undo my work. That's a pretty big leap. Like that's the key to the problem here. Let's do this back again. Okay, so we've made a couple of right angle triangles on purpose here. This right here would be a right angle triangle. This right here would be right angle. This right here would be right angle. There's right angles everywhere here because these things are like perpendicular to each other. If this is 30 and that's 90, this guy would be 60. But if this is 90 degrees right here and flat is 180, then this angle here must also be 30.
I didn't realize that you drew
So if I want to find FGY, that's going to be 147.15 cosine 30, because it'll be the adjacent you're solving for.
Why would you find FGY?
You're right, actually I don't need to find FGY, do I? Let me do it anyways, but you're right, it wasn't necessary to the question. Good point, Raj. Times cos 30. So this would have been 127 newtons basically. So it's getting pulled into the middle basically at 127 newtons, which would also be the normal force. So both of these guys would have been 127 newtons. That doesn't actually solve my question though. So if I want to find the FG in the x direction, it would now be 147.15 sine of 30 because we're looking for the opposite. I got 74 basically.
Is that 0.5 or 0.15?
Sorry, that's 0.15. I missed a dot in there. Okay, I only get 2 sig digs because 30 degrees only had 2 sig digs to it. So this should be 74 newtons, I believe. Did you guys get that as well?
Yeah.
So what this means then is that the FGY was 74 newtons. Therefore, the force of friction must also have been, I can't even do this, yeah, 74 newtons. That is what we were looking for. We were looking for how much friction must there be to keep this box in place. That's what we were looking for, yes. Yeah.
You don't need direction. Will it just
No, I guess you could say like, I don't even know how you'd give it a direction. I guess up the slope, maybe, if you wanted to give a direction. Like, there must be 74 newtons up the slope. Yeah, something like that would make sense.
Yeah, no, that's what I realized, like,
Did taking the picture and turning it like slightly slanted, did that help keep track of where things are? I hope.
I didn't even know there was a picture on the back until like halfway through the
Oh, never mind. That explains things then. Sorry, I often try to put in like extra slides where I put like, where is it? This slide has been intentionally left blank, but like sometimes it actually puts it on like the next page, so it doesn't hurt to look ahead. I try to leave you more room. Okay, was that last example okay? Okay. You're gonna have to draw your own inclines from now on. So,
Is it okay if we draw them how we tilted it?
I'm okay with that. I'm actually gonna show you a method though of solving it where you don't actually like need to tilt it. So, I'm okay with if you do what we just did there, where you actually draw it with a tilt. I'm okay with that though. Okay, so let me draw a picture here. We've got a 28.5 degree incline. So I'm actually going to draw it flat this time, though. I'm not going to draw it on a tilt. This is 28.5 degrees. And there's a box on it, which is 5 kilograms. But this time around, I'm actually going to tell you the frictional force. So we're not solving for the frictional force. It experiences 2 newtons of friction. 3 newtons of friction. Sorry. Eyes are playing tricks on me. So that would be like this way here. You have a force of friction of 3 newtons. What other forces, though, are acting on this box? Well, okay, so gravity is pulling straight down. Okay. Gravity pulling straight down. There's also, if you need to find it, which we don't in this example, but there is a normal force, which is going to be like at an angle off to the side there. And what we could do is we could break gravity back up again into gravity y and gravity x. But like, since I haven't tilted this thing here, it may not make sense to use x and y. So another convention, this is what I was taught, and I found that it worked well. Rather than calling this FGX, I called this the force D, force downward, which basically would be like the force that is causing this thing to slide downhill. Does that make sense? So if you wanted to do that rather than FGY, that'd be fine. Like, I don't care what you call it, so long as you can solve for this side right here, because this is what's pulling the box downhill. And then rather than calling FGY, sometimes this is referred to in textbooks as the force. It's an upside down T. You might see that. I don't care what you use for symbols, just so you know. Like, you could use a smiley face and a star for all I care. Okay. But I just want to show you some common conventions. This symbol right here stands for perpendicular. Sometimes some books will do force perpendicular, which is like the perpendicular force to the actual surface. I don't care what letters you use, okay? That's not relevant. Just make sure it's clearly labeled. Okay, one more thing. The angle right in here, though, is also going to be 28.5 degrees. I can give you that as an always. Okay. If this angle here is 28.5, this angle right here would be 90 minus that, which makes this angle right here, again, 28.5. So I'd like to solve for the downward force then, or the X gravity force. I don't care what you call it. So that's going to be... Actually, I'm still missing a number though, aren't I? I need to find what gravity actually was.
Which is 49.0.
Okay, so let me put that off to the side. To find the Fg, it's going to be mass times gravity. It's going to be 5 kilograms times 9.81. What'd you say?
49.05.
Okay. So I do have to actually find how much force gravity is pulling directly down. So that would be the hypotenuse right here. Okay. I want the downward force, or whatever you want to call it, the FGX, whatever works best for you. So that's going to be 49.05 sine, because it's the opposite, of 28.5. Okay, I got 23.0653, etc. So 23. Oh, I messed up here. Sorry, let me try that one more time. 49.05 times by sine 28.5. 23.4. Okay. So this would be 23.4 ... newtons. That's how much is actually getting pulled downhill. That's why I like to call it FD. That's what I was shown. Okay. So this FD right here pulling down is 23.4 newtons now. Okay, so gravity is causing 23 newtons of force to go down the hill, but friction is pulling backwards with 3 newtons backwards. Perfect, yeah. So you'd say like your net force would be equal to the downward force minus the frictional force. So gravity's trying to pull this thing down at 23.4 newtons. Friction is 3 newtons. So the net force is 20 newtons basically. 40467 newtons.
20.4.
40463, something like that. Okay, that's a 3. What was the question? What were we asked? Okay, so now that we have the net force, F net is equal to mass times acceleration. We have the net force. We also know the mass, so we got to use that again. So I guess what you could do is take this guy now and divide by 5 kilograms, and that would give you your acceleration. I would say down the incline. It's probably the best way of putting it. Because like down would imply like directly down, and this would be like down the slope. So you may need to be a little bit more specific. So I got 4.08. I only get 2 sig digs though. So I got 4.1 meters per second squared, and then like say down the incline. That might be the best way of putting it.
Why did you divide the 20 by 5 kilograms?
Okay, because this is 20 newtons, and then 5 kilograms times acceleration.
Oh, the newtons.
So to get acceleration by itself, you got to divide by 5 kilograms
Oh, I see.
to get A by itself.
Okay.
Does that make sense? If you want to tilt this whole thing sideways, I'm fine with that too. Like, that's not wrong. Okay. This is just, I'm showing you the way I was taught. I was taught to call it an FD for like how much downward force there is, and F perpendicular for how much like into the block force there was. Fn would then be equal to F perpendicular. We don't usually care about finding Fn or F perpendicular. Those usually aren't relevant to the question. Again, I don't care whether you call it F smiley face, Fy, Fn, F perpendicular. I don't care. Just make sure I can understand it. And make sure you can keep track because you've got numbers everywhere. Heather?
I have a question for the next question.
You're a little ahead of me. Okay, any questions on this one? This is our last one, I think, right? Okay. Okay, last one. What's your question?
The 850 newtons.
Yeah.
But, like, I don't really understand how that.
Ah.
That's
Okay, can I get started first here, and then I'll bring that up when I get to it. Okay, so same concept here. You've got your hill, 35 degrees. Snowboarder, I'll just use a box. A box is more than fine. Again, what forces are being applied to the snowboarder? Okay, gravity goes straight down. Friction is pulling you backwards. Not that we need it, but there's a normal force. When you break gravity up into its components, just so you guys know, I'm going to go with F perpendicular and FD from now on. But again, I don't care what you use. I often then draw the FD over here as well, just to remind myself that he's getting pulled downwards by partial gravity. He's getting pulled backwards by friction again. So most of your diagrams kind of start like this.
Wait, which one's FG? That's
Sorry, FG would be like this side one here. Let me change where that is. Just take that out of the middle there. Okay, Heather, your question was about the 850 newtons. Okay. Sometimes rather than giving you a mass of something, I will give you it in newtons, which means that like this 850 newtons right here is its gravitational force. Okay. So like if I tell you his mass,
Also, if you divide that by 9.8, what do you get mass?
yeah, if you want to find mass, then we can actually do that by saying, well, if Fg is equal to m times g, this will be 850 newtons equals mass times 9.81. So if you divide by 9.81, now we actually do know his mass. So his mass is actually 86.646 kilograms. That's a little twist that I could play in a question, is rather than actually giving you the mass, I'm going to give you how much gravitational force he has, and you've got to actually work backwards and find the mass. So, let's set a few other things up here. I now know that this guy right here is the 850 newtons. And this angle right here is the 35 degrees. I could find the force perpendicular, but that's not really relevant in this question. But I could find the downward force. So to find the downward force, it'll be 850 times the sine of 35. So that's, I got 47.5399. 5399.
Wait, how'd you get that?
850 times sine of 35. The 850 was the hypotenuse here, and then FD is the opposite, so then I picked sine of 35. Okay.
I was talking around.
Now this one's a bit question.
I just wondering why he gave us time. So he's got
Yeah. So you guys are kind of maybe looking at these numbers here going, why are those there? Okay. This question's a little bit different here. He's not stopped. He's moving. So is his force of friction equivalent to the downward force? No. Because he's in motion. Does that make sense? So we need to actually now do something like this. His net force is equivalent to the downward force we just found, subtract the force of friction. And we're looking for this, so this is what we're solving for. So we now know the downward force. We need to try to figure out his net force. And that's where those other numbers come back in. Net force is equal to mass times acceleration. We do have his mass, because we just found that a little while ago. 86.646 kilograms, but we don't know his acceleration.
But you have seconds.
But we have some other numbers though, don't we? So I'm just going to put a little note here. We need to find acceleration. Because here's our process. If we find acceleration, we can plug acceleration into this formula here to find your net force. Once we find our net force, we can plug that into here to find our frictional force. So it's very much like use this to solve, get that number to solve again, use that number to solve again. So,
Why did we use 9.81 to find the mass? Just because it's like.
because what I gave you here was I gave you his newtons, which would be like his FG. So then I used 9.81 because like on a flat, like ignore the fact that he's on an incline, he always weighs the same mass. So he always has the same like force of gravity pulling him down. Okay, we gotta find acceleration. I gave you a distance and a time. So distance was equal to 14.5. Time was equal to 6.25. There's also one more hidden piece of information. I did tell you the velocity initial was 0. So I now need a formula that can find me an acceleration based on that. Yeah, same one we've always used. So d equals VIT plus 1/2 AT squared. We gotta find his acceleration. A lot of work, eh? Pretty typical though. 14.5 equals 0. That's kind of pointless because he has no initial velocity. Plus 1/2 of a, and then time we got to square. So how do we get a by itself? I would times by 2 on both sides, and then divide by 6.25 squared. You could do like 1/2 of 6.25 squared, figure out what that is. I got 19.53. And then divide 14.5 by your answer. That's what I got. Good. 0.7424.
So don't you have figures for that?
Well, I'm not going to use sig digs until I'm done. So like I'm going to keep all of these numbers and plug it into here to get my number for F net. Once I get that F net, I'm going to plug it into here, and then I can finally find out how much frictional force there actually was. So working backwards, your F net is now equal to your 86.646 kilograms times by this acceleration we just solved for. $86.646.27931 times 0.7424. So I got a net force of 64.326 newtons when I times those numbers together. Okay, so then I would then say that that is now equal to your FD minus FF. What was FD? 487? That probably works best. Yeah, so your 64.326 newtons equals, what was this guy? I just forgot it already. 487.
Subtract that.
0.5399 minus FF. So some people are suggesting maybe the best way of doing it is to like bring FF to this side over here and then subtract the 64 the other way. So your final answer will be the force of friction is the 487.5399 newtons minus the 64 this. Whatever that was. 487.5399 minus the 64.326. So I got a final answer of 423 newtons. And I do get, I only get 2 sig digs. Shoot, I should have done 37.0. I'm gonna cheat, guys. 37.0 is the new angle. I should give you 3 sig digs here. That way we can actually keep 3 sig digs when we're done.
What about 35 degrees is that?
That's what I said, 35 degrees, let's make it 35.0.
Oh,
37.
Oh, what did I say? I do that all the time. Make it 35.0 just so that I get 3 sig digs. I didn't think about that when I wrote the question. Because otherwise you'd have to make it 4.2 times 10 to the 2 newtons. So. Long process, eh? I would say it's like, it's death by 1,000 paper cuts. Like, none of the individual steps are probably all that tricky. Like, most of them are very straightforward formulas. F equals ma, not that hard to work with. Fg equals m times g. The key though is you've got to keep what's going on straight in your head, if that makes sense. The problem solving aspect of physics is probably the hardest part. It's not the actual math, but the problem solving part.